Hopefully you're starting to get more practiced at reading slopes off of graphs. So let's have a look, because that's all we're doing. We're looking at a slope of Vx versus t, which is all we mean by this equation. So we have an initial part where the slope is negative, and that's a constant slope, so we should see a constant negative value of ax. And then we should have a constant positive value of ax, because this is a constant positive slope. And then we should have a 0. And that is what we have here, constant negative, constant positive, and 0. And so the answer is A. I think it's worth stopping at the moment and just noting a pattern that we're seeing. We had a Vx_av, an average x component of velocity, which we could get by a delta x over delta t. And you can think of that as a rate of change of x with respect to t. In other words, for every unit change in t, how much does x change? That's the rate of change. Well, you can also think of it as a rise over a run, a rise delta x divided by a run delta t, and then you're thinking of it as a slope on the x versus t graph, connecting 2 points. That's not necessarily the slope of the curve you're interested in, it's a slope of a line connecting the 2 points. Similarly, Ax_av is a delta Vx by delta t, so it's a rate of change of Vx with respect to t. For each unit time, how much does the x component of velocity change by? And again, it can be thought of as a slope of a line connecting 2 points on the Vx versus t graph. And because these are both slopes of lines connecting 2 points on the graph, they're average rates of change. Well, if you have any old relationship, some variable thingy, which is some delta A over delta B. I don't know what A and B are, whatever they are, thingy is the ratio of their changes. Then thingy must be an average rate of change of A with respect to B. And if you graph A versus B, the slope of a line connecting 2 points on that graph must be thingy. If you don't want average rates of change, then if you're able to let these deltas get very small, you're able to approximate the slope of tangent lines to the graphs. And now you're looking at rates of change that aren't average. They're what we would call instantaneous rates of change, and we would note them as derivatives, like so. We have one more piece of unfinished business from last lecture before we move on to constant acceleration. We reasoned that Vx, which is the slope of the x versus t graph, was decreasing for this graph. And that told us that ax, the x component of the acceleration, is negative. And notice that that's because of the shape of the graph. Because the x versus t graph curves downward, that makes Vx decrease. The terminology you may learn in calculus is that this graph is concave down. And we can conclude that any time our x versus t graph has a shape like this, curving downward, ax must be negative. Well, we can flip that around and think about a graph with this shape. Now, if you draw a few tangent lines to it, you can see that it's getting steeper with time. Or in other words, Vx is increasing, and that tells us that ax is positive. Similarly, this one, I've already drawn 2 tangent lines to it, and you can see they're negative and they're getting less steep. Well, that means Vx is increasing because it's getting less negative. And so again, ax is positive here. And so look at both of these graphs and you see they are both curving upward. So if the x versus t curves upward, or you would say it's concave up, then ax is positive. This motion of the cart up and down the incline turns out to be an example of a very important special case, which is motion with constant acceleration. Notice that the Vx versus t is pretty much a straight line. And so one of the consequences of that is that no matter what time region you use, whichever delta t you choose to get your acceleration, you're going to come up with about the same answer. And so the average acceleration is just the same as the instantaneous acceleration. So we can just drop the average. Now that's going to turn out to be really handy, and so whenever we can approximate the acceleration as constant, it'll be useful to do so. One of the reasons uniformly accelerated motion is so important is that it's so common. Throughout this course we're going to see lots of examples of it, but a particularly important example that you come across often is freefall, and we've already seen an example of freefall because we've looked at this falling ball. And if you look at the v versus t, vy versus t graph, you can see it's roughly a straight line, and that's the hallmark of constant acceleration. Let's see one of the features of freefall that some people find surprising. Here's a 100-gram mass and a 500-gram mass. Do you care to predict which one will hit the ground first if I drop them both at the same time? So if you're in my course and you're accessing this video via Moodle, you will now be asked this question and you'll answer it in Moodle before going on to the next part of the lecture. If you're not in my course, then I would encourage you to come up with an answer to this question before clicking on to the next video.